In the previous video, we discussed how the attention mechanism works. We saw that for certain nodes, connections to certain neighbors might be more important than the others. And we also discussed the basic formula used for computing the attention coefficient, which is a score determining how important a particular connection is. Here, WHI and WHJ are the transform node embeddings for any neighboring node pair I and J, and alpha is the attention mechanism. It turns out there are many different approaches that you can use to compute the attention coefficient. So there are many ways to structure the attention mechanism. And the attention mechanism that we are going to study is from the original graph attention network paper. And here is a big picture overview of what the attention mechanism looks like. The attention mechanism uses a shared single-layer neural network, and these are the various components of that neural network. Remember that the attention is computed for each pair of neighboring nodes. Now, the input to this attention network is the transformed embeddings for a pair of nodes. This is the input to the attention mechanism, and the final output of the attention mechanism is the normalized attention coefficient. And it's important to note here that the attention coefficient is normalized across all connections. Now, why is this normalization important? If you were to use the default unnormalized or raw scores, this is what the attention coefficient might look like for each connection. So between 2 and 1, the coefficient is 2.4. Then between 2 and 3, it's 3. Between 2 and 4, it's 7, and so on. If the attention coefficient is not normalized, the relative values may not make sense. And basically, it's hard for you to compare the attention across the different connections. It's important that you use normalization to scale all of the attention scores so that they lie between 0 and 1. This normalization of the attention coefficient is a part of the attention mechanism. So now, with this in mind, let's go back to seeing how the attention coefficient is computed. Now, here is the mathematical formulation of computing the attention coefficient, and here, of course, is a big picture overview. Let's see what happens here step by step. The input to the attention mechanism is the transformed embeddings for each node pair. These transformed embeddings are concatenated together, so this double pipe sign that you see represents concatenation. These concatenated embeddings are then passed through the attention weight vector. The attention weight vector is just a neural network layer of learnable parameters. The output of this neural network is then passed through a LeakyReLU activation function. Now, the LeakyReLU activation function serves to emphasize the positive relationships that exist between nodes. If you remember a visualization of how the LeakyReLU works, for positive values of the input, the LeakyReLU just outputs the input itself, so f of y is equal to y. For negative values of the input, f of y is equal to alpha y, where alpha is a very small value, so negative values are kind of suppressed and positive values are emphasized. This emphasizes positive relationships between nodes. The output of the LeakyReLU gives us a normalized attention scores. These have to be normalized so that their scale could lie between 0 and 1. And this is done by a Softmax layer. You've likely encountered Softmax as a part of regular neural network building and training. The Softmax layer scales down the unnormalized scores so you get normalized scores in the range 0 to 1. It's important to note here that while computing attention between node pairs, you only consider neighboring nodes. That is, you don't compute the attention for all pairs of nodes in your graph structure, but only for nodes that are directly connected. And this computation of attention is referred to as masked attention, because you're not computing attention for all node pairs.